Welcome back to another lecture. In this lecture, we want to talk about mass timber design. Basically, made of glue lam and CLT panel, cross-laminated panel. Mass timber making a comeback in the United States. It's good, big in Europe, and it's the push is a lot bigger than Canada, and it's making toward the U.S. And really, if you're an engineer, you want to go ahead and get ahead of the curve and learn about this stuff. And today we're going to talk about how we're going to design a floor panel CLT and how we're going to design a wall panel for a column also for CLT. But before we go ahead and continue, let's talk about the some introduction. What is the mass timber? Basically, if we look at the CLT panel itself, there are a number of them. They are nail laminated timber, they are glue laminated timber, and you have the laminated veneer, and there's also dowel laminated timber, and then you have the cross-laminated timber CLT, which most everybody uses. Of course, CLT was first patented in France in mid-1980s, and then later on was developed in Germany in 1990s. The thickness of individual lumber pieces may vary from 5/8 inches to 2 inches, and the width may vary from 2.4 inches to 9.5 inches. So your CLT panel are two-way slabs, and the stronger direction follows the grain of the outer layer. That's okay. The outer layer is the important one. For example, when we use a wall, CLT is installed so that the board on the outer layer of the panel have their grain running vertically. When CLT is used in a floor and roof application, panel are installed so the board on the outer layer run parallel to the span direction. So CLT panel are stacked up in a different layer, and there are variation like of 9-ply, 7-ply, and 4, 3, 5, and 7-ply variation. We will do some example on here. And another thing I want to talk about, the really the code that we're going to use for CLT panel is that they have a CLT handbook, which is they've done a great job on it, and it's a lot of good reading there. There's still room for improvement, but they've done a great job. Then we have the PRG 320, which is basically the standard performance rated for cross-laminated timber. We're going to use that, and the NDS only have 1 or 2 page on that, but mainly you want to follow the CLT handbook for the United States if you are in the United States. So we want to let's design a floor panel here, and say we have this panel. It's about 20 feet long and probably by 8 feet or 10 feet wide. So to make the panel, let's say let's make it 10 feet wide by 20 feet long, and the load we're going to design it for, we're going to have 50 pound of live load for like office building, and give it a dead load of 40 pound per square foot, and we're going to make this to a 90 pound per square foot the load. Normally when we calculate this the uniform distributed load, we have to multiply that by the turbidity width. In this case, because we have the whole panel, and we're going to just go ahead and cut out a 1 foot section of the panel. So out of the whole panel, if I have a panel right here of a CLT, and for the design I'm just going to cut a 1 foot section out, and we're going to analyze that, and we're going to design it this way, which will represent the whole thing. Now, the panel we're going to be thinking about, it's going to be you have 3 layer, 5 layer, 7 layer. We're going to go with the 3 layer, and each layer is about 1.1 3/8 thick. So that will be H1. Your total thickness is going to be 5 times that, which comes out to 686.875. And your width that we to cut out here, we're going to use a 12-inch width. And we're going to go ahead and use the CLT handbook code and PRG and PRG 320 and NDS also. All right, let's get to work. So the first thing when I have right here, I want to calculate really this design is very similar to beam design. We're going to go ahead and do the bending and check for bending. Then we're going to check for shear. Then we're going to check for deflection, and then we're going to check for bearing. Then we're going to go ahead and do the wall. So let's go ahead and do this floor panel. Let's calculate the maximum moment of this. Of course, maximum moment for bending moment, it's going to come out WL squared divided by 8. And that is 40 plus 50 is 90. I got 90 time L, my L is 20 squared. 20 squared, and divide that by 8. I will get 4,500 pound foot per foot. Okay, because we're doing per 1 foot section here. Our MB should be less than or equal CD, CM, CT, CL, and then FB, SFF section, effective section modules. Now, normally we have these are, because of the inside condition, all this comes out to 1, and in here we don't have any snow load. It's all live load and dead load. Let's say CD is gonna come out 1, and this is basically provided by the manufacturer. This is given by the manufacturer, and this is basically FB times SFF is basically bending moment. We learn, we know FB is equal M divided by S, or MB, bending moment, is equal FB times S. So basically this is the bending moment which is given by the manufacturer. We'll continue with our problem. So now we have our bending moment for this load comes out to 4,500, and therefore we can go ahead and calculate this right here. This is going to come out to 111, and FB is given by the manufacturer from table A2, and that is 10,400. So this comes out to 10,400, and if you look at the unit, it says pound foot per foot. Because we did per linear foot. And our came out 4,500, so 4,500 is less than 10,400, and that checks out. So step 1 checked out. Let's go ahead and do step 2. Now we're going to check for step number 2, which is a shear. And if we go per NDS 10.3 or the code from CLT handbook, we have the shear is V should be less than or equal FS time IBQ divided by Q effective, and this normally is given Q prime effective by the manufacturer. Of course, that comes out to let me put this on a board, and this has to be V less than or equal CM. We got CM CT, and then we have this FS IBQ divided by IBQ effective, and that's going to be this basically is all commonly normally is 1, and this is given by manufacturer. So basically we can say that's almost is equal 1 time VS, which is given. Okay, so our shear comes out to WL divided by 2 right here. WL divided by 2, which comes out to 90 times 2 times 20. then divide by 2, that's equal 900 pound. So that's our share, and 900 is less than, and if we go to table A2 from the PRG 320, we have VS is equal 2480. So this is less than 1 time 2480, and that checks out, so our share checks out. So that was step 2. Step 3, let's go ahead and find the deflection. 1/8 time WL squared time K, and K usually is given, it's 6/5, time K divided by GA effective. And so most of this stuff is given from the table. So let's go ahead and figure it out. Delta short term is equal 5 divided by 384 plus W was 90 multiplied by 20 times by power 4. Convert this to inches, we're going to multiply by 12 inches by power of 3. Remember when we talked about here, we said this is a pound per foot per foot. So divided by EI effective, and EI effective was given from the table, comes out to 444, that's time 10 by power 6. And from table A2, and plus 1/8 time W20 90, I lied, and that's time 20 squared time 12 time, we said it was 6/5 for K. 6/5 divided by the GAF comes out to 0.92. 0.92 time 10 by power 6. So my delta comes out to, I don't know, 0.8 something. I think 0.73 plus 0.8 something. This number, double check this number. I think 0.83, or I didn't bother calculating it, but I did this one. This is really not much here, so this is the one really you want to worry about. So that comes out to less than, if you want to do L over 240 for 20 foot, which is 1 inch, it's okay. You can check the long term if you wanted to, but if you use that, make sure you use the K factor, use 2.0 for creep. Okay, so we did step 1, step 2, step 3. Let's now check for bearing. Alright, so from CLT handbook section 2.5, which has both basically perpendicular to the grain and then parallel to the grain. And let's check out the weak section of it, which is perpendicular to the grain. It says P should be less than or equal, not equal, less than or equal, yeah, F prime perpendicular C, and that time A. Now be careful, your A area is not the cross-sectional area, it's your bearing area. So if I'm going to have this panel right here, it's going to rest on this ledge right here. That's where it's going to ledge. That's what I'm going to worry about right here. This distance, that's my bearing, that's my LB. So that's where the panel is going to rest, and that's going to be your width. It's going to be 12 inches. So your area is going to be 12 inch we already have, and how much of that 12 inch that you're going to have, say for example this notebook is about 12 inches and it's a panel, how much of it's going to rest on here, how much distance here it's going to rest on. So that's LB. Normally we learn from for beam design, you use either 3-inch. If you use 3-inch, use a factor. But in here, they said the factor is 1 anyway, so don't worry about it. And if you use 6-inch, factor is 1. So if you use 3-inch or 6-inch, let's say we're going to use 3-inch or 6-inch, doesn't matter. We can go both 3-inch and 6-inch. So if I go 3 inches, it'd be 3 times 12. And that comes out to, if I find it, 36, right? So I got 36 right here. And then I have a P should be less than or equal. And my compression from table A1 of the PRG 320. Of course, this F prime C, it's the compression factor is going to be your F prime C. It's equal all the factor, which is going to come out to 1, CM, CT, CD, then time the compression itself, the compression stress, and that from the table came out to 650, I believe. Let me see, I have it. Yeah, 650. Okay, so that come out to 650, so we're going to use 650 for that. This is all come out to 1, and that's a 650. Then we have 650 multiplied by 36, and that's a large number. And your P is basically the reaction from here, which will be 900 pounds, which is way less than that. You have 900 less than 650 times that number is large number, so that checks out. Okay, so this was with the panel. Let's do the wall. If we want to design a wall, give me a minute to erase there, and then we're going to go ahead and do a wall. All right, let's go design a column, and we're going to design make a wall and design this wall to be able to support to 80 kips of per foot of floor. And one of the things we're going to look at it at the CLT handbook section 2.2, which is on the board here. We're going to worry about this column factor, a column stability factor, CP. So we're going to find the our PCE, which is the Euler equation for critical buckling, and then we're going to find PC, which is a composite compression design capacity. And once we have that, we also let's go ahead and find this, and we will get to work. Let me get a different color here. So first thing I want to find out is the PC, which is P critical buckling, which comes out to the Euler equation, pi r squared time EI apparent minimum, I'll talk about that in a second, divided by effective length squared. And let's find out how we can find EI apparent. But before we find this, we got to find EI apparent by itself. So the EI apparent is given by equation EI APP is, which is the basically the effective bending stiffness EI effective, and is adjusted to become apparent. This is to count for the shear deflection. And the reason we do is, so EI a column stability factor, we first got to find the critical buckling. To find critical buckling, we got to find the apparent stiffness factor of EI minimum. But to find the apparent stiffness factor, you basically take the EI effective, you multiply the factor to count for shear deflection, and it's basically that divided by EI effective divided by the modulus of shear rigidity and time L squared. Let's go ahead and calculate this. That comes out to pi, well, I gotta find out the give me a minute. I got it. So I have this big number right here that comes out, this all given from the book, the E2, comes out 440. Divide that by KS. KS is 11.5, and that's from table 2. It's on the screen right now. And time 440. And then divide that one, you gotta be 1 plus right here. And divide that by GA came out to 0.9. And then time 20 squared. Time 12. So what I got, that comes out to 402. The minimum apparent bending stiffness, which is EI APP-MIN, and that's equal to, by the spec right there, 0.5184, and multiplied by EI APP, and if we multiply this by 0.402 time 0.5102, 0.5184, and that will give me 208.4 pound inch square. Now if I come back in, calculate this, I have this right here, so my P critical going to come out to plug all this number right here, PI squared, I got EI, and L, my L was 10 by 12, which said this make this wall 10 foot tall. Okay, and that comes out to pi squared time 208, and divide that by 120 squared, 10 times 12 square, and remember this is got to be multiplied by 10 by 6, so that comes out to 104 pound. Okay, make sure you multiply this by 10 by power 6. Okay, so now we have got that. We have that. We're gonna find a PC, and our PC P star C comes out to is compression stress multiplied by the parallel area. See if I can spell that. PA, you know what I mean. So that, and F prime C from a table comes out to 1800. So now my P star comes out to 1800 multiplied by the area, and the area was right here. We have each individual 1.375, and there was 5 layer, we said, time 12 time 5 layer, and that comes out to 148,500. Okay, now I have this, and C is given to be by the code. It says right there 0.94 CLT. So C is the 0.94 CLT. So if I calculate all this stuff right here, and PC divided by P, it comes out to 196. So PCE divided by P star comes out to 142. 690, divide that by 148, 500, and that's 0.92. So this equation comes out to 1 plus 0.92, divide that by 2 times 0.9 minus square root of 1.96 divided by 1.8, square that, minus 0.96, divide that by 0.9, and I get CP is equal 0.727. Great. Okay, so now we found all this. Let me erase this so I can finish it up right here. So our F prime C times area of parallel area is equal to what we have right here we calculated, which was FC. We have that, and we have CP, which we have that, and times the area, parallel area. Now I have 1800. That comes out to 1800 times CP was 0.727. 0.727 times the area. So it's 1800. Let me write down here 1800 times 0.727, and my area, we're going to use 5 layer. Okay, it's important here. So I got 1.375 each height of each layer times 12-inch hour width times 5 layer and time 0.72 1800. So that give me 107,959 pound. Okay, and that number is, so 80,000 pound we have here, it's less than 107,959. Now you gotta one thing you gotta keep in mind is here, if I go ahead make this to a 3-layer wall, that number is going to be less than 80,000. That's not going to make it. So this is how you do it basically. When you do the floor plan, you just do like beam analysis. You check for bending, you check for shear, you check for deflection, you check for bearing. With these things, the bearing is not the issue, and they normally give you way more than enough, probably 3 to 6 inches. And for column, for wall design, and they're pretty strong. They can take a lot of load, like we saw here. But the most important thing is you got to find the stability factor right here. That means you have to find these equations just went through here. I hope this was helpful, and if it was helpful, push that button, subscribe. Thank you.